So the first thing I want to point out, yeah, fine, we have a quiz this after this in the lab, but I also want to point out that so the exam. So I updated the lecture schedule, and I'm suggesting. I don't want to sign in. It's October 19th, basically. So I don't know where's the.
So 2 weeks?
Yeah, October 19th. Okay. So we'll probably be done with the full wave rectifier, so that it will cover everything until the full wave rectifier, probably, which is the full wave rectifier. You will find it very similar to the half wave rectifier from a waveforms and equations perspective. I mean, you did the homework on the half wave rectifier, right? So you're able to calculate the capacitor for in cases where you have a capacitor rectifier, you're able to use the equations for the current waveform, calculate beta. You're able to do this kind of stuff. Okay, I mean, really, if you're able to do that, I mean, the full wave rectifiers solutions will be almost similar, almost identical. The only thing that will be different will be the waveforms and maybe some terms in the equations, few terms in the equations. So it's not much different. That's the full wave rectifier. So hopefully so the exam will cover both. So the exam will cover until end of chapter 4. That's the plan. Yeah. So October 19th is the exam. That's the current plan. Okay. That being said, we'll start covering the full wave rectifiers chapter. Again, it's a rectifier, so it's an AC to DC converter still, right? So that's still what we're doing. We're going to cover the single phase, uncontrolled with diodes, like we did before for the previous chapter for the half wave rectifiers, and then we will cover the controlled version of the single phase rectifier. And then we will look at the three-phase rectifiers, also uncontrolled based on diodes, and then controlled based on SCRs as well. And then we will talk about some applications of controlled three-phase rectifiers in the power system. A few applications of those. Okay, so that's the flow. I think we will go through in a similar fashion. So we'll go through the equations. I mean, all the waveforms first. You feel comfortable with those, and the equations are pretty much identical to what we had before because the current waveform is exactly the same, right? As soon as you have an RL circuit, I mean, you impose a voltage across an RL circuit, you will still see the same shape of current rise and then fall based on the time constant. So that's why nothing changes really. So the only thing that changes are really the waveforms and the circuits. But the equations for current will be very similar, right? So we'll go through so the most important things are the waveforms, to be able to understand the waveforms for the different circuits. Yeah. So you may have seen the full bridge rectifier, full wave or full bridge rectifier, whichever you want to call it, in single phase fashion drawn this way before. Maybe in 325 you saw it drawn this way, for example. Yeah. Whether it's this or this, it's the same. So this is just nothing but a redrawing of this circuit. Yeah.
Believe it or not, our 325 professor skipped the diode spot. Yeah. Like he didn't teach diodes at all.
In College Station, he skipped that. Wow. Yeah.
Yeah, we saw that one in lab. That's what you start off your.
The project.
Yeah.
You work with the project. Anyway, we'll go through it. I mean, it's very similar to the half wave rectifier with a few tweaks. Yeah. So let's look at what's happening here. So this is an AC source. Okay. Let me actually redraw it here, so we can go through waveforms. So we'll have our AC source here, and then we'll have our 4 diodes drawn this way, and this will be our output resistive load. This is my source connected to the first leg, and then connected to the second leg. Okay, and then this is plus minus the output, and then this is initially we'll do the R, and then we'll do the RL and a source. Exact same thing. That's why it's very similar to the last chapter. You will not find too much new besides the waveforms and the circuits. but the explanation for the waveforms will be very similar, so it should be a good review for what we did last chapter. Okay, so our input waveform looks like this. This is my V input, this is my V input. So if this is V input, for the positive half cycle, for the first from 0 to pi, what's going on? From 0 to pi, this point here is positive, right? With respect to this point here, correct? So this is the most positive potential in the circuit. This is the least or the most negative potential in the circuit. If you look at them, if you hold the voltmeter with the positive node, with the positive probe here, the negative probe here, you will see this waveform or a oscilloscope. And if you flip the probe, what would you see? If you flip the probe, you will see the opposite, right? Correct? Okay. So this would be the most positive potential in the circuit. This would be the most negative potential in the circuit for the whole half wave, for the whole from 0 to pi. So from 0 to pi, we have some mode of operation for the circuit because of this phenomena. So what's going on? If this is the most positive potential and this is the most negative potential, then what do you think is going to happen in this circuit? So let's say this is diode 1, this is diode 2, let me see how they number them here. 1, 3, 4, and 2, sorry. One, and then this is 3, and then 4, and 2. This is how they number them in the textbook. Yeah. So what's going on in the first half cycle? I would like to draw my V out, my output voltage. So this is the most positive potential in the circuit, right? Then definitely here, this node here is less positive, right? This node here is less positive. So this is the most negative potential in the circuit. Then definitely this node here is a little bit more positive. Okay? So if this is the most positive potential in the circuit, right here, can this diode be on? This diode cannot be on because I have the most positive potential right on top of it, right? So I'm actually reverse biasing it using the most positive potential in the circuit. So this diode 4 will probably not be on. How about 1? 1 can be on. What's the condition for it to be on? If I am able to, if I connect my circuit, I would see positive current flowing. If positive current would flow and the voltage is such that I'm not reverse biasing the diode, then the diode will conduct, right? So I have my circuit, which is this resistor here, and the voltage here is such that this node has a higher potential than any other node in the circuit. Right? So hence diode 1 can conduct, since if I connect it, current will flow through diode 1 where? Into my resistive load, right? And if diode 1 is conducting, can diode 3 conduct? It cannot conduct because if diode 1 is conducting, it's connecting the most positive potential in the circuit to this node. If it connects the most positive potential to this node, diode 3 is definitely reverse biased. I'm reverse biasing. As soon as diode 1 turns on, diode 3 is reverse biased because I'm placing a high positive voltage at this node versus this node. So diode 3 cannot be on, and diode 4 cannot be on because they are seeing the highest potential or the most positive voltage in the circuit on this side, right? So they're seeing the most positive potential here, most positive, so they are not able to turn on, right? Diode 1 was able to turn on, right? How about my return path? This is the most negative potential in the circuit. If this is the most negative potential in the circuit, that means diode 2 is able to turn on as well. This is the potential here is going to be much more negative than anything else in the circuit. So this will be a little bit more positive than this potential, since this is the most negative source potential. So diode 1 would turn on, and diode 2 would turn on in this case, and the current would return back to my source, right? So current has to go back to the same source, right? So current found the path through diode 1 and diode 2 in the positive half cycle. How about the negative half cycle? We can redraw the circuit. It's the same way?
It goes all the way through.
No. How come? No, let's draw it again. Yeah, let's redraw it. Now the supply flips polarity between pi and 2 pi, right? So this is the most positive potential in the circuit now. And this is the most negative potential. Right? So if this is the most positive potential, then I have 1 here, 3 here, 4 here, and 2 here. Right? So this is the most positive potential in the circuit. So 2 will be reverse biased. And this is the most negative potential in the circuit. So 4 can probably turn on. It can probably be forward biased. So 4 can be forward biased, assuming there is forward current flowing through it. And since its polarity, its direction is this way, then current can flow from the load back through 4, right? And then what? Which others are turned on?
One's off.
1 is off because 3 sees the most positive potential here, right? So 3 can turn on. And if 3 turns on, it's placing the highest potential, which is the source supply voltage, here. So it's turning off 1 as well, right? So in this case, 3 turns on. So current flows through 3, through the load, and back through 4. So from the source and back to the source. Oh, sorry. So from the source, so this way, from the source, through diode 3, through the load. So the direction of current in the load does not flip. You never flip the current direction in the load, which means the voltage polarity in the load is always the same, right? Which is what we want to do. That's DC. We want to go from AC to DC. We would like to rectify. So we want to make sure we are maintaining the same current polarity and voltage polarity in the load, right? So in the first half cycle, diodes 1 and 2 are on. In the second half cycle, diodes 3 and 4 are on. Okay? So this is what's going on. So what does the output voltage look like? So if diode 1 and 2 are on, what does the output voltage look like?
Same as the input.
Exactly. So it's the same as the input. The circuit basically looks like this, right? Right, so it's going through diode 1, coming back through diode 2, and this is my resistor at output. Right, so this is what my circuit looks like. How about in the negative half cycle? It looks like the same thing, basically. Right, so in both cases, I'm taking, but I'm flipping. In the negative half cycle, I flipped the terminals of the source. Right, so I basically flipped the terminals of the source, but kept the same terminals of the load, right? So I flipped the terminals of the source. So this became my negative, this became my positive. So I'm going, so if I draw my equivalent circuit now, the circuit looks like this. So this is my resistor, blah, blah, blah. Okay? So I basically flipped, all I did was flip the terminals of the source. So in the positive half cycle, my output voltage will look like my input source exactly. And in the negative half cycle, it will look like the inverse of my input, which is this red waveform, right? So it will look like this full wave rectified waveform. Right? How about current? For the resistive load case?
Yeah, scaled down version by R.
Exactly. So I output will look exactly like V output, except it's, it will be scaled down by V max over the R value. How about the voltage across diode 1 and 2? Yeah. So diode 1 and 2 initially 0. And then it will, depending on the polarity, so let me draw it nice. So this is diode 1, for example.
Will it not go up, like right there, to switch it high?
So here, initially they're on, so the voltage is 0. And then they're off. When they're off, what do they see? So let's, it's off. So what does this see? At one side, it has this supply terminal, right? And then 3 is on. So on the other side, it sees the other supply terminal, right? So it's seeing the voltage at the input across it, right? Do you see that or not? At one side, it has one of the supply terminals. And then, because 3 is on, the other supply terminal is now across diode 1, right? So it's seeing the supply voltage placed across it. It just depends on the polarity we decide for the diode, right? If we say that this is the positive and this is the negative, then it sees the negative of the supply voltage. It sees the opposite of the supply voltage. If we say this is the positive and this is the negative, it sees the supply voltage. Does not really matter, right? I mean, it's, at the end of the day, it depends on, if I give you this and I ask you for the voltage across the diode, I have to draw the polarity across the diode for you to do that, right? So if I draw it such that this is the positive terminal and this is the negative terminal, right? Then it's seeing what? It's seeing the negative terminal of the supply here and seeing the positive terminal of the supply here. So it's seeing opposite of the supply. But it's exactly the same, right? It's going to see either this waveform or this waveform depending on the polarity that I put here. Right? I think in the textbook they use the polarity where they put the positive here and the negative here for the diode, and they draw this as negative opposite of the supply voltage. I believe they do that. Let's see. 1 and 2, yeah. No, they actually draw it as a supply voltage. Okay, but they didn't put the polarity here, so maybe it's in the textbook. I don't know. I mean, you have to. I mean, this depends on the polarity that you choose for the VD, right? So let's see if they do it later. No. Yeah, they typically put positive here. They're typically putting the positive terminal here, yeah. So if you put the positive terminal here, let's look at our drawings. If you put the positive terminal here, negative here, it's seeing what? The negative voltage here and the positive voltage. This is the positive terminal of the supply, right? It's placed across the diode here. So I have, this is VD. This is my diode here. And I'm seeing the supply voltage put across it this way. This is the polarity of VD. So VD looks like this, right? And then the supply voltage is supply voltage polarity is what? It's like this, but it's negative, right? So that means that VS plus VD is equal to 0. So VS equals to minus VD, or VD is equal to minus VS. So it should be this way. Anyway, it's the with the way that, again, for me it doesn't really matter if it's if you draw it this way or this way, because it just depends on what polarity you use for the VD here, right? The most important thing is what? What's the peak value of inverse voltage across the diode? Or how would you select this diode? What's the peak voltage rating of the diode? Vmax, right? It's equal to the input voltage peak as well, right? It's basically seeing the full source voltage placed across the diode. That's basically what we get from here. And same thing with D2, right? Because what? 4 is on, diode 4 is on, so the negative supply terminal is down here, right? And the positive supply terminal is here. So when 2 is off, it also sees the positive supply terminal here and the negative supply terminal here. So it also sees the full supply voltage across. Okay? So that's the full wave rectifier with a R case. So what do you think is next? So we did the output voltage, output current, diode voltage, and of course for diodes 3 and 4, it's the opposite, right? So it's initially it will have some voltage across it, and then they will be 0, right? So 3 and 4 will be the opposite of 1 and 2. So everybody's okay with that? Okay, so now what? What's the next circuit? RL, exactly. So same diode rectifier, full wave or bridge rectifier, but instead of R, we put an RL. One, two, three, four. So what will change? So I have my same input voltage. This is V input. I would like to draw V output. I would like to draw I output.
Draw your current first.
Draw my current first. That's fine. I can do that. So how will my current look?
You exponential start and then fall at some point beta.
So let's draw the resistive current first, because I don't want to. So you don't get confused. Okay. So if we draw the resistor case, my output voltage looked like this. I'll just draw the resistor case in dotted form. Okay. My output voltage looked like this, and my output current looked exactly the same but scaled. Okay. So now, how do I go from here to the RL case?
Draw your current flags.
Okay, so it will start here. Do you agree that it will start at the beginning, but it will rise exponentially, and then?
It'll follow the path and fall at some point beta that is determined by the size of your inductor.
Is it gonna fall down to 0? What's happening in the second half cycle?
No, it's not.
You remember the freewheeling diode case that we had?
It's going to go back up.
Exactly. This is very similar to the freewheeling diode case. So what happened in the freewheeling diode case? I was not. I mean this freewheeling diode started picking up as soon as the voltage tried to go negative in the single phase rectifier. The freewheeling diode picked up the current. So what's happening here? So here 1 and 2 are initially on, right? Diodes 1, current is flowing through diode 1, and then through the load, and back through diode 2. Okay, and then as soon as the voltage tries to go negative, right? As soon as the voltage starts going to negative into the negative half cycle, I have these two diodes acting like that freewheeling diode that I had before. Similarly, right? Because as soon as the voltage tries to flip polarity, diodes 3 and 4 will kick in. They will automatically they will automatically start conducting. And if diodes 3 and 4 start conducting, then diodes 1 and 2 will stop conducting. Right? So the output voltage will look like what? I mean, can can the voltage, if the voltage goes negative or the current tries to go negative here, what's going to happen? All these diodes are pointing up. All these diodes are pointing up. So it's not possible for current to flow in the reverse direction. It's not possible. It's not possible for current to flow in the reverse direction. So current will not flip polarity. We agree? Current will not flip its polarity. Current can lag, maybe, but if it has the proper conditions to lag the voltage. Like voltage may go negative and current be lagging and still positive. That's fine, if the conditions exist, right? But let's see what's happening here. So as soon as we go into the negative half cycle, diodes 3 and 4 will act like that freewheeling diode we had before. And if diodes 3 and 4 conduct, we said that as soon as 3 conducts, 1 will stop conducting. As soon as 4 conducts, 2 will stop conducting. Right? We went through that just now. So if 1 and 2 were conducting, we were getting this output voltage waveform. How about if 3 and 4 are conducting? We're getting this. Right? So is it going to change now in the RL case? The output voltage, will it change? The output voltage will not change. The output voltage will stay the same. It will still be the full wave rectified voltage. Yeah, so how does this change the current? Okay, so now how does this change the current? Because now my inductor now, my RL circuit now has a positive voltage put on it again.
How does your voltage go to zero? Like, wouldn't it not ever touch zero?
No, it will touch zero because it's.
But with an inductor,
current may not touch zero, but voltage will touch. Right, because the voltage, it's the voltage of the input source. Now either the voltage of the supply is going through, it's crossing the zero. So, and it's because it's trying to cross the zero that this diode 3 and 4 started to pick up. Right, so acting like the freewheeling diode that picked up, in the single phase rectifier, when the voltage was looking like this for the RL case. As soon as we added the freewheeling diode, it removed this. Remove this part. It stopped at zero. The voltage stopped at zero. And the current was still flowing in the circuit because it was flowing through the RL and the freewheeling diode, right? We had the freewheeling diode across an RL. Yeah? So as soon as we put this freewheeling diode, as soon as the voltage tried to flip across the RL circuit right here, the freewheeling diode picked up the current. Right? And that's what's happening with 3 and 4 here. As soon as the voltage, so 1 and 2 are conducting, as soon as the voltage tries to flip polarity, 3 and 4 pick up the voltage. So they start conducting. If they start conducting, then the output voltage, if 3 and 4 are conducting, 1 and 2 are not conducting, then the output voltage will look exactly like the case with the resistor case, with the output voltage. But how will the current react? The current reacts differently, right? So the current for the resistive case was this dotted line. How about for this RL case? If I had a half-wave rectifier, okay, then I didn't have this part here, right? If I don't have this part here, what would have happened? The current would have gone up, and then it would have gone down at some point beyond where the resistive current would have ended, right? We agree to that. Okay, that's fine. So now, what did I add? But in that case, I had 0 voltage here, now across the RL circuit. Now I'm placing a positive voltage again across the RL circuit. Exactly, it will never go down, it will go up again. I'm placing a positive voltage across the RL circuit, right? So if VL is a positive number, VL is equal to LdI by dt, right? So if VL is positive, then dI by dt has to go positive again. Right? So it was going negative for a while, but because I've applied this positive voltage across the RL circuit, then at some point this current waveform will flip its slope and rise again and fall beyond where the resistive load would have fallen. But then I'm applying the positive voltage again across it, right? So it will never fall to zero. Okay? Yes, sir.
This change in slope happens at t equals pi, right?
No, it does not happen at t equals pi because It happens when the inductor voltage is positive, not the RL voltage is positive. Because here I have RL, the V output is positive, I agree. The V output, so the combination of the voltage here is positive, right? But what is VR? So V output is equal to VR plus VL. So VL is equal to V output minus VR. So it depends on the value of VR. So where VL becomes positive depends on the value of VR. So I have some simulations, I think, like time domain simulations that will show it will not happen exactly at 0. It will happen a little bit later depending on the value of R and the value of current through the resistor, because that will define VR, right? If R is very, very small, it's going to happen where? It's going to happen closer to the pi. Or if R is very small or the current is low, it's going to happen closer to pi. If R is a little bit larger and current is higher, it will happen a little bit further away, right? Because V output is small initially. V output is 0 initially, right? So if V output is initially 0 and VR has a value because there's current flowing in the circuit, then what? Then VL is negative. So for a little bit, VL is negative. Initially, VL is actually negative. It was negative. It was negative. That's why the current was falling down, right? But then at some point, V output starts to increase, and the current was falling down, so VR was decreasing. So the combination becomes positive. So VL becomes positive again. Right? So this is what's defining the flipping point. Okay, so okay. Okay, so now, how about the current flowing through now? So the current flowing through diode 1 and 2 would be this current here, right? Now the current through, let's say, I'm drawing the current flowing through diode 1 and 2 would look like this, and it would stop here. Current flowing through diodes 3 and 4. This is ID1 or ID2, right? ID 3 and 4 would be 0, and then it would look like this, right? Do you agree? This is ID 3, ID 4. Yes? Because initially, again, diode 1 and 2 were conducting in positive half cycle. Diodes 3 and 4 conducting in the negative half cycle. Right? So this is diode 1 and 2 current. This is diode 3 and 4 current. How about if I ask you to draw the supply current? What would the supply current look like? What would the supply current look like? This is probably not in the textbook, right? So you have to, the waveforms that I asked about are not necessarily the waveforms in the textbook. They're the waveforms that you have in the circuit, right? But the textbook may be drawing a subset of the waveforms, right? This may mean, that's why when I recommend you simulate the circuit, look at the current and voltage waveforms everywhere, and try to understand how they look like, right? So what does the supply current look like? So let's see, supply current is this current here. Do you agree? So this current here is coming into where? This is diode 1. This is D1, right? And this is what? D4, right? And this is supply current going back, right? From D3 and then D2. So I have two nodes here, right? So supply current is coming in here. This is IS, and this is IS, right? Negative IS. So if this is IS, so IS is equal to what? Current is going to come into this node from the supply and then out through D1. So this is ID1. And this is what? Coming into this node is ID4. It can only come into the node because it's because of the diode. It's a unidirectional device, right? So IS plus ID4 is equal to ID1. IS plus ID4 is equal to ID1. So IS is equal to ID1 minus ID4. ID4 is 0 only in the first half cycle. In the negative half cycle, it has a value. So what does IS look like? What? Yeah, IS is the input. What does it look like? What does the IS current look like? I'll draw it here. In the first half cycle, it looks like what? Exactly. It looks like ID1 and ID2. And then in the negative half cycle, negative ID3 and ID4. Okay, negative. Right. So it's something like that. Okay. I supply. Can you find the equation for this current easily? Or this current? Can you find the equation for this current easily? Or this current easily? This current. It's not the same as what we had in the last chapter where we had alpha or the inception angle at a certain point, extinction angle at a certain point, and you were able to find the differential equation defining the current between them, right? We had an example in the last chapter where we had a funky waveform for current as well. So what did we do in that case? We looked at what is accessible to me. What's accessible to me is the voltage. I know what the voltage waveform looks like. This is this half-wave rectified waveform. It's a periodic waveform. Sorry, it's a full-wave rectified periodic waveform. So I can use Fourier series because I can easily I know the equation for this voltage waveform. So now from the Fourier series of the voltage waveform, which is the full-wave rectified waveform, which you have in the sheet for the Fourier series, you could take your Fourier components for the voltage, divide them by the Fourier components for the impedance, and then get the Fourier components for the current. So we did an example. We went through an example like that last chapter, and this would be a similar case because here I don't have an easy way to find the equation for current. The equation for current is difficult to find. There's no closed loop solution I can easily find, right? So this is the RL case. Everybody's okay and comfortable with the RL case? Yes? No? Supply current, you can find supply current. Write it down, right? Draw your nodes. This is my node, current's coming in, current coming out. Write your nodal equation. It will make life easier for you. So it's basic circuits, but write it down. Don't try to memorize the waveforms. Okay, so now what do we do? RL and a source. Okay, so the progression is similar to what we did before. So we do the full wave with the RL and a source. One, two, three, four, R, L, VDC, V input, and this is my V output here. And we draw our waveforms again. It's my input voltage waveform. And this is my DC source. Okay, so now let's draw the output. So what's happening in this circuit? So that's the R case. R case, the V output looked like this. Right? And In the RL case, also, the output looked the same, right? So now what's happening to the RL and a source case? And let's output current. Output current will be interesting as well. Why? Because this point becomes interesting. Why is this point interesting?
That's technically where it'll jump over and start following your input voltage as opposed to your DC.
It's only when the input AC source is higher than the DC source will current be able to flow through diode 1 into the load, right? So before this point, there will be no current flowing in the circuit. So what's the output voltage? It's my DC voltage, like the previous case. Good. And then what? And then current starts flowing from this point, meaning diode 1 starts conducting, and I'm connecting my source input to my output voltage. Current passes through 1 and goes back through diode 2, right? So in this point here, current starts conducting, and then what? Then what's going to happen? For the resistive load case, current was doing this. For the resistive load with a source case, right? If I have the resistive load and a source, what would the current have done? Resistive load and a source.
It would have just been in that little section between the two where the VN was higher than.
Exactly. So from this point, there will be current. And it would stop here. We agree? So for the resistive case, only with R with a source. This red is only R without a source, okay? So R with a source case is this blue dotted line. So now I have RL with a source. So it's definitely, it's going to start here, because this is where the AC source is greater than my DC source. And then it will not stop here. It will stop somewhere beyond that, right? Somewhere beyond that. Somewhere beyond that can be somewhere here, for example. Can be before pi. Or, depending on the value of L, can be after that. If it's after that, what happens? So let's look at the case where it's at this point. What happens to the output voltage? Follows the input, and then
Still follow the input.
Because until the current ceases to flow, right? So until the current ceases to flow, to follow the input, and then there's no current flowing. So my output voltage becomes my DC source voltage again, and I repeat the loop. Because what's happening in the negative half cycle? What's happening in the negative half cycle is that now I'm flipping the source, right? It's like flipping the supply. So now this point is the critical point where the resistor, for the resistive case or for the RL case, the current will start conducting again. This would be a critical point. So until this point here, so I didn't draw this input nicely. So until this point, the output is what? VDC, right? And then the output is equal to the input until current stops flowing, and then goes back, blah blah blah. Okay. Now you can complicate it a little bit, right? If my value of L is large, or if my value of the DC source is low, they're very similar. If the value of the DC source is high, what is it going to do? If I increase the value, in the same case, same RL, but I increase the value of my DC source, what will it do? What? Is it going to impede the current from flowing, or is it going to allow, is it going to help the current flow meaning move this point to the right? Or is it going to impede the current from flowing and move it to the left?
Move to the right.
If I increase the DC source,
Oh,
increase
the
the
DC source?
yeah, increase the value of the DC source. Increase the
So
value
move it over to the right.
to the. This is right.
Yeah.
But if you increase the DC source, you're impeding current from flowing, right? I mean, you're opposing the source, the AC source that's creating the current flow. So if you oppose that, then you bring this point to the left.
But if you're raising your DC, that's going to make it higher, and it's going to move your point where it's higher over to the right.
To here?
Yeah.
But I don't care about here. I'm talking about here. I'm talking about the extinction point. Extinction point. Sorry, extinction point. Sorry, I agree. If I raise the DC source on the left-hand side, fine. It will start later. I agree with that. That I agree with. So I was talking about the extinction point. Extinction point of the current. Is the extinction point of the current going to move to the right or to the left? To the left. You're opposing current flow, right? It's opposite of what increasing the inductance would do. What would increasing the inductance do? Help maintain current flow. So it would move it to the right. Decreasing the DC source would move this to the right. Increasing the DC source will move it to the left. Decreasing the value of inductance will move it to the left because it becomes more like a resistor case. Right? Okay. So, I think they have all the drawings in the slides for now. So let's look at the drawings that they have in there. So we went through this case, the R case. We drew all the waveforms for the supply. I didn't draw the supply current for the R case only. I think it's the same sort of idea for the RL case. I'm going to go through this circuit. I forgot to go through this one. But for the RL case, we drew the supply current, right? This funky waveform for the supply current. So hopefully this is clear to everyone. And they drew the different diode currents as well. And, fine, when you increase the inductance, we know that I can do that if you want. So for the RL case, current looked like this, correct? We went through this waveform. So if I keep increasing inductance, what happens? At some point, it will rise, for example, and then the inductor, if it's infinitely large, the current will just be flat. It will not change, right? So forget about the initial transient. If the initial transient, initially the inductor had zero current, blah, 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 forget about that. In steady state, because they don't draw the transient here, in steady state, the fictitious case of an infinite inductance would mean that this value of current will be just flat, right? That's a fictitious value. And if it's flat, then what does diode current 1 and 2 look like? Just a flat square wave. 3 and 4, flat square wave. How about the supply current? Flat square wave positive, flat square wave negative, right? It's flat positive, flat negative, right? So that's the case that they have here. Is it okay with everybody? It's the RL case, but with a very large inductance. Just keep increasing the inductance. What happens? Current never changes. Current never falls down. Never falls down. Just continues going straight. Yeah. Continuous current. Yeah. Then they do the piecewise simulations for this, and then they do the RL with the source case. We did that, and we saw the current falling at some point. So we saw the current falling at some point. And if the current falls, they call that it's called discontinuous current case. And we said that if I decrease the DC voltage, what happens? Then I'm decreasing the opposition for current to be maintained, right? So current can continue to a point further beyond the resistive case, right? Or if I increase the inductance, it's the similar sort of effect. Current will be maintained. You're helping current to continue to flow, right? So in that case, if I continue to increase the value of inductance, what's going to happen? So let's look at this discontinuous case, because we went through the waveforms for that. If I continue to increase inductance here, what happens? This point will move to the right, to the right, to the right, to the right, until what point? Until the point where the DC source intersects the AC source again, and I'm putting a positive voltage again across the output voltage, across the output branch, and that which means at some point the voltage across the inductor will become positive again, right? In that case, I will have the continuous current. I mean, it's the same, similar to what we had before for the RL case, pure RL without the source. Except when you put the source here, it changes some of the dynamics. I mean, it's let's look at I would like to make sure that everybody's clear on this. So here the current stopped at this point, right? In this case. If I increase L, what happens? Okay, and sorry, it stopped here. How about in the negative half cycle? Negative half cycle current starts here again and flows until this point, correct? And I have discontinuous current, right? This is output current and it's discontinuous. If I increase the value of my inductance, what happens? This point moves to the right. This point moves to the right. At some point, for a certain value of inductance, the current will fall beyond where this starts. And this starts where? This starts where the DC source is equal to the AC source, right? Similar to the full wave rectifier with an RL case that we went through. If this happens, then the current becomes continuous, right? So the current becomes continuous, right? If the current becomes continuous, is there any point in time where, if I'm saying the current's continuous, there's no point in time where the current here is coming into this branch is zero. So if there's always current flowing, can the output voltage be VDC? When was the output voltage equal to VDC? When current was not flowing. So now the output voltage is not going to be VDC at all. It's always going to be equal to the input voltage, right? So only at the beginning when you're first ramping up, and that's what they draw here. So only at the beginning they have a little bit of a VDC here, right? So if I decrease VDC or increase L, I have the similar effects, right? If I increase L, I'm allowing the current to, or forcing the current to change slowly. That's increasing L. Current is forced to change slowly. Or if I'm decreasing VDC, so here they brought VDC down to a very low level versus a very high level here. So decreasing VDC also helps amplify the effect of the L more, because now this VDC is a lot less and it opposes the flow of current a lot less. So if it opposes the flow of current a lot less, for the same value of inductance which is trying to maintain the current, then the current will become continuous for certain values of R and L, right? So there are two effects that can make this happen. And I recommend you simulate it, right? Simulate the circuit and then play with the DC source value for the same value of RL, and then keep the DC source, and then just keep increasing the value of L, and you will see that the same effect will happen, right? So is everybody okay with these waveforms? Okay. Here in this simulation, I simulated because they don't show the value, the waveform of VL, for example, VR, which is what you were confused a little bit about, right? So here I actually show the value of VL and VR. So this was VL, and this was VR, and this was the output voltage. So it's nice to put all the waveforms together on the same plot so that you can help explain what's happening. So I recommend you do the simulations, but they're in here for you. What else? Before we go to the capacitor, there was one circuit that I skipped here. This one. So it's called the center tapped transformer rectifier, and let's see how this one functions. So everybody's okay with this? No? You okay? So let's see how this works. We have a source here, and we have a transformer that we have center tapped. They can basically place the tap at the middle of the winding. Okay, and this is diode 1 and diode 2, I think that's what they call them. Yeah, 1 and 2. Minus plus the output, and this is my R. Okay. So we agree that current will only flow this way and this way. So that means current will always be in this direction in the output, right? So I'm satisfying my AC to DC conversion, right? The polarity of current in my load is never changing. So I had AC at the input, but my output has current in a certain polarity, fixed. So it's DC. So now what's going on? This is a transformer. Let's say this is a 1:1:1 ratio, for example, right? So this circuit here is like what? It's as if I drew something like this. Where this is Vs and this is Vs. They're identical. Do we agree that these two are the same? They're equivalent? They're equivalent, right? This is 1:1:1, right? So if this is Vs, this is Vs, and this is Vs as well, right? So how would this circuit function? So in the positive half cycle, what's going on? What's happening in the positive half cycle? This is Vs. So Vs and Vs, they're exactly the same. They're identical. So what's happening in the positive half cycle? D1 is on. Can D2 conduct? This is the most positive potential. This is the negative potential. It's a positive potential, negative potential, right? So this is seeing a negative potential, the most negative potential by the source here. So it cannot conduct. D2 will not conduct. So D1 will conduct. So if D1 conducts, this is like a short circuit, and I'm doing what? I'm placing my output voltage across my load, right? So the output voltage equals to Vs. So V output in the first half cycle, V output is equal to Vs, and D1 is conducting. How about in the negative half cycle? In the negative half cycle, the voltage, yeah, this is positive, this is negative. This is positive here, this is negative. Right? So this diode can conduct, this diode will not conduct. This diode's an open circuit, this diode's gonna conduct. If this diode conducts, I'm basically taking my Vs as well, but after I flipped its polarity, I'm placing it across V output. Right? So I'm placing my source across my V output, but I flipped its polarity. Right? The polarity of the source has flipped here. Right? So it's, and the diode that's conducting in this case is diode D2.
How is it not zero? Because I mean, you're taking the V source of the top one is at that node, and you have V source of the bottom one just at the opposite node. So you have two positive.
But this is an open circuit.
No. Oh yeah. All right. So
Right?
yeah,
It's an open circuit.
Yeah, that one wouldn't flow.
It's an open circuit. Right? So in the positive half cycle, D1 is on. Negative half cycle, D2 is on. Right? So everybody's okay with the fact that D1 is on in the positive half cycle, D2 is on in the negative half cycle? Okay, so if D1 is on in the positive half cycle, then current will flow initially through, the output current will look like what? Output current in the resistive case will look exactly like the output voltage, so it should be the output current, and this will also be, if I wanted to draw only ID1, then ID1 would look like this, correct? And then 0. How about the voltage across any of the devices? Now that's the important part. Voltage across the device. So let's see what's happening. So if let's say we're in the positive half cycle. So in the positive half cycle, ID1 is conducting. So good. The voltage across it is 0. That's good. So this is V across D1. It's 0 in the positive half cycle. Now in the negative half cycle, it's an open circuit. Not so fast. Let's open this. Let's open this up. And we're trying to find the voltage here. So I have, remember, I have a V source here. Is this here or not?
Yes.
Even when it's open, it's here. And then this V source is now being applied across V output as well. So this exists, right? So this V source exists, right? So let me take this loop here, right? For me to find, I can find the voltage across the device here, because I can take this loop, Kirchhoff voltage law around the closed loop, right?
But if you're talking the second negative half cycle, or in the
Negative half cycle, this is on,
yeah,
so it's
the-
just short circuit. It's a short circuit. This diode is short circuit, and this VS exists, and this VS exists.
Your arrow, like, it's going down, but not.
No, remember, for voltages and currents, when we do the Kirchhoff, when we're solving circuits, instantaneously the value of the voltage, yes, is negative in the negative half cycle, but the polarity, remember, we have to assume a certain polarity and then calculate and then see if it's positive or negative. If it's positive, then it's in the same polarity. If it's negative, it's in the opposite polarity, right? Maybe I confused you a little bit with drawing these pluses and minuses, right? It was just to show, okay, which diode can conduct, which diode cannot conduct. But if you're doing Kirchhoff voltage law around the loop, you cannot change the polarity of the source between the positive half cycle and the negative half cycle, right? So this is the polarity of the source. It just happens to be a negative number. That's fine. It just happens to be a negative number. Both of these happen to be negative numbers in the negative half cycle. That's okay. But this is the polarity of the source. And if I define a certain polarity for this diode, for example, I don't know. Let's say I define this. Let me define it as the opposite. Easier. So let's define this as the polarity of the voltage across the diode. So what is the voltage of diode 1?
Yeah.
V out? Is it? Remember, let's say, if you want to take this loop, we can take this loop as well. But if you take this loop, you have V out in the loop as well as the source. And if you take this outer loop, you have these two sources. And if you take V out in the loop and this source, V out is equal to what? Vs, right? So you always have two sources. Right? There are two components that are opposed by this diode, that this diode has to block. So what is the voltage across this diode going to look like? Kirchhoff voltage law. This is Vs and this is Vs, guys, right? So exactly, it's 2 Vs, right? So it's Vs plus Vs is equal to Vd1, right? Vs plus Vs is equal to Vd1, right? Or Vs plus V output is equal to Vd1, right? It's double the voltage, right? So whether you draw a positive or negative, I don't care again, okay? But right? But this is 2 Vmax. If this is Vmax, this is 2 Vmax. Is it okay with everybody? Okay? So this is VD1. How about VD2? Okay, it's 2V max, but in the positive half cycle, right? So this circuit is really nice because it gives me the full wave rectification that I would like, with 2 diodes instead of 4, right? And which is neat. The problem is the diodes here have to be rated for double the voltage. If for the same output voltage and for the same input voltage case, of course, right? For the same output voltage and for the same input voltage, the diodes here would have to be rated to double the voltage, which is fine. I mean, buying a diode, if you would have to go on the vendor's website, for example, and compare buying 4 diodes that are 30 volts versus buying 2 diodes that are 60 volts. I'm pretty sure that buying 2 diodes that are 60 volts will be cheaper than buying 4 diodes that are 40 volts. The limitation is, of course, here you need a transformer as well. Actually, in most cases, when you connect to the utility, you will have to have a transformer. So that may be something that you will have to have anyway in both circuits, right? So if you do the numbers, this is not a bad circuit to have. It's a nice circuit to use. Yeah. So it's called a center tapped rectifier, center tapped full wave rectifier. The current waveform, of course, is the same, right? Nothing changes for the current waveform versus the full wave rectifier output, right? So for the resistive case, the I output looks like this. For the RL case, RL guys, RL, full wave rectifier RL. We just did this. What does the output current look like? So this is the resistive case. So the RL case will be, the current will fall theoretically delayed, right? So if it starts here and it's going to fall theoretically delayed, but this is the full wave rectifier circuit, right? So I am putting a positive voltage again across it, so it's always continuous, right? So for the RL case, for the full wave rectifier, current is always continuous, always continuous. If you add a source, you can add this continuity to the current, because there will be something that's going to oppose that inductor's effect. So it can push this point to the left, and then you will have a discontinuous current. But for the full wave rectifier, current is continuous. Current is always continuous in the output. Okay. How about the supply current? Go back and do it, right? I'd like you to go back and do it. Well, what do you think it's going to look like for the R case? It's going to be ID1 in the positive half cycle and ID2 in the negative half cycle. So it's going to be a sine wave. For the RL case, to be it will have the same funky shape that we had in the RL case for the full wave rectifier, except that I would like you to go and do this, and draw. Make sure you understand it. Yeah, like draw the supply current here, and make sure you understand this effect of the transformer's effect. It should not be difficult. I mean, at the end of the day, it's going to be a sine wave for the resistive case, and it's going to be this shape. This shape, remember, it stops here, and then because it's continuous, so this will be in the positive half cycle, negative half cycle to have this funky shape. So this will be supply current for the RL case. I supply same as before, same as the RL case we had before. So now what we did was, but they don't do the RL case here, by the way. In the text, they don't do the RL case for the center tapped rectifier. But again, it's something you can look at. Yeah. So we discussed basically. So we went through this circuit, the full wave rectifier and its waveform, resistive load, and then resistive load for the full wave rectifier that's center tapped. The only difference between them is the voltage rating. RL load, full wave rectifier. For the large inductance case, a fictitious case, we went through that. And then RL in a source case, continuous and discontinuous, we went through that. And then next time we'll do the capacitance output and then start looking at the controlled rectifier. It's exactly, I mean, I hope you see that, I mean, the waveforms look very similar to what we did before. They are very, very similar, yeah. So we'll stop here, and next time we'll continue the waveforms, and then we'll do the equations after that, like we did for the last chapter. So as I said, exam will be October 19th. I updated the lecture schedule to reflect that. It will probably cover until the end of chapter 4, which is the full wave rectifier. So we still have 2 weeks, and we will cover this chapter early next week. We'll probably wrap up this chapter.